Evolution of atomic theory. Humans have been trying to determine what constitutes an atom since the time of the ancient Greeks. In 5th century BC, Democritus' atom was atomism, which means all matter is composed of small invisible particles called atoms. The word atomism derives from the ancient Greek word atomos, which means that which cannot be cut into smaller pieces. In 1803, John Dalton's model of atom was solid sphere. He stated that atoms are invisible and compounds are combination of different types of atoms. In 1897, J.J. Thomson's model of atom was plum pudding. He stated that an atom is a sphere, but the positive and negative charges are embedded within it. In 1911, Ernest Rutherford's model of atom was nuclear model. He stated that electrons orbiting in a set predictable paths around fixed positively charged nucleus. In 1913, Niels Bohr's model of atom was planetary. He stated that electrons are arranged in concentric specific circular orbits around the nucleus. In 1926, Erwin Schrödinger's model of atom was quantum model. He stated that the locations of the electrons could only be described as being part of a cloud around the nucleus. Let's see here Erwin Schrödinger model of atom. Wave mechanical model of atom. The atomic model, which is based on the particle and wave nature of the electron, is known as wave mechanical model of the atom. This was developed by Erwin Schrödinger in 1926. This model describes the electron as a three-dimensional wave in the electronic field of positively charged nucleus. Schrödinger derived an equation which describes wave motion of an electron. The differential equation is d square psi divided by dx square plus d square psi divided by dy square plus d square psi divided by dz square plus 8 pi square m divided by h square into e minus v into psi equal to 0, where x, y and z are Cartesian coordinates of the electron. The Cartesian coordinate system is based in three straight axes x, y and z. These three axes form three planes: the xy plane, the xz plane and the yz plane. A point in Cartesian space is symbol represented as a string of three numbers x, y, z. In this equation, where m mass of the electron, e total energy of the electron, v potential energy of the electron, h Planck's constant and psi wave function of the electron. Definition of Schrödinger equation. The Schrödinger equation, sometimes called the Schrödinger wave equation, is a partial differential equation. It uses the concept of energy conservation, that is kinetic energy plus potential energy equal to total energy, to obtain information about the behavior of an electron bound to a nucleus. It does this by allowing an electron's wave function psi to be calculated. By solving the Schrödinger equation gives us psi and psi square. With these we get the quantum numbers and the shapes and orientation of orbitals that characterize electrons in an atom or molecule. The Schrödinger equation gives exact solutions only for nuclei with one electron, that is hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus, carbon 5 plus, etc. In mathematical language, we say that analytic solution for psi are possible only for one electron systems. Schrödinger equation has two forms: a time-independent Schrödinger equation and a time-dependent Schrödinger equation. The time-independent equation considers the electron's quantum state to be unchanging. Hence, it considers the electron as a standing wave. The time-independent equation allows electron densities, that is, the sizes and shapes of atomic and molecular orbits, to be found using chi-square. The p orbitals here is the examples of chi-square. Chi-square represents the probability of finding the electron at various places in a given region around the nucleus. Chi-square varies from one region of space to another. Hence, the probability of finding electron in different regions is different. The time-independent Schrödinger equation can be expressed in highly compressed mathematical shorthand as h cap psi equal to E psi, where h cap is a mathematical operator called Hamiltonian. Schrödinger gave a recipe of constructing this operator from the expression for the total energy of the system. The total energy of the system takes into account the kinetic energies of all the subatomic particles, that is electrons, nuclei, attractive potential between the electrons and nuclei, and repulsive potential among the electrons and nuclei individually. Solution of this equation gives E and psi. This equation, the Hamiltonian h cap, doesn't change over time. Hence the term time independent. And also this equation is used to solve problems that involve stationary states, such as the structure of atoms and molecules. This equation says the sum of the wave functions kinetic energy and potential energy equal to the wave functions total energy. The time independent equation can be written in any suitable coordinate system, such as Cartesian coordinates x, y, z. For hydrogenic atoms, spherical polar coordinates are more suitable. Hence, just h square divided by 2m Laplacian square psi r plus b r psi r equal to E psi r. Hamiltonian operator containing kinetic energy and potential energy terms, where h is the reduced Planck constant, m is the electron mass, Laplacian is the Laplacian operator, psi is the wave function, v is the potential energy, E is the energy eigenvalue, r denotes the quantities or functions of spherical polar coordinates, are theta, pi. In this equation, where v equal to E square divided by 4 pi epsilon naught r and Laplacian square equal to dou square divided by dou x square plus dou square divided by dou y square plus dou square divided by dou z square. By substituting these values in the above equation, the Schrödinger equation in spherical coordinates becomes dou psi divided by dou x square plus dou square psi divided by dou y square plus dou square psi divided by dou z square plus 2m divided by h square E minus v psi equal to 0. When Schrödinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions psi of the electron associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers: principal quantum number n, azimuthal quantum number L, and magnetic quantum number m, arise as a natural consequence in the solution of the Schrödinger equation.